So now that we have an idea of how this Euler's method works, we're going to take a look at what that accumulated error can look like. And so in order to do this, we have to have kind of the correct answer to compare to. So what I've got here is the actual solution curve. This thing right here is the actual solution curve. And we're going to go out to x equals 3. We're going to take the solution curve out to x equals 3. So that's what the actual solution looks like. And again, Maple can tell us what the actual solution looks like. But our predicted solution looks something like this. We started here, we took one step, then we took another step, and then we took a third step, and we wound up right about there. This is what our approximated solution looks like. So we predict that y of 3 is right there, but in actuality it's up here. And so you can tell that the actual solution is quite a bit different than what we actually see. And the gap here, the gap between these things, is what we would call our error. My marker's starting to die on that one, I guess. So the gap between those two tells us we're not so great. But of course, this error is particularly bad because our step size was huge. So what happens if we take smaller step sizes? Well, this is the same graph, but with a couple of different step sizes. Here's a step size of 1. So this is the solution that we had from before. There's 1, 2, 3 steps. But a step size that's even smaller, something like 0.2, so a fifth of 1, would create a whole bunch of smaller steps, but it would get to this spot right here and would be much, much closer to the exact solution. So keep in mind, a step size of 1 meant we had to go 3 steps. That means 3 different calculations. But if we decided to go with a step size of 0.2, this would mean a 1/5 is our step size. And that means in order to cover the same distance, 3 units, we'd have to do 5 steps for each 1 unit. 5, 10, 15. This is 15 steps. So if you can imagine doing 15 of those calculations, you could get a pretty accurate answer. Now, if you wanted to be really crazy, you could do a step size of 1/20th. But if you did 1/20th, then that means there's 20 steps here, 20 steps there, 20 steps there. That means you'd be doing 60 steps in order to get there. But look at how accurate 60 steps is. 60 steps is so close to the exact same, or the exact answer. That's a really good approximation. So what's the trade-off? Well, more steps means more calculations, but it also means better accuracy. So with Euler's method, it's a trade-off. Do you want to do more steps and more calculations and be more accurate, or not? And so at the top of the next page it says, so why not just choose really, really, really small steps? So there's the first reason, and this is the reason that most people catch on to pretty quickly, is more steps, smaller steps, leads to more steps, which means more calculations. And of course, more calculations also leads to something. This also leads to more time. Now, you might not think of it this way, but your computer actually does take time to do these calculations. And let me give you just a kind of example of what this might look like. So for example, if you said you have a step size of, I don't know, 0.1, and that corresponds to a computation time.